with electron configurations, guys, is it's kind of like the home, quote unquote, where electrons are. All right, so it's where they're found. So when we write out these configurations, think of it like an address as to where the electrons are located. All right, so that's kind of the analogy that we are going to use. So guys, electron configurations are a dashed chain of numbers that are found in your lower left corner on your periodic table. So this is in the new packet that I passed out today. They tell us the number of energy levels as well as the number of electrons that are in each level. All right, so they're telling us how the electrons are arranged around your nucleus. That's really what they're telling us. It's kind of a brief synopsis of what they are. All electron configurations that are on your periodic table are considered to be neutral, meaning what? What's neutral mean? No charge, and kind of take it a step further, what does it mean about your subatomic particles? Which two are equal? Protons and electrons. Good. Okay. For ions, so when you do have a charge given to you, you either add or subtract the charge from the last number in the configuration. So I'm going to give you guys a minute to kind of copy that down, and then we'll kind of take it to the next step. So guys, if we look here, lower left corner, those dashes, you are given the electron configurations on your reference table. You don't have to worry about what to do with them. You just have to know what they mean and how to apply them. So if I were to just look here in my box, how would I know how many electrons that a single element has? Total.
Subtract the number of protons from the mass.
Nope, that's neutrons. All right, so how do I just know how many, just in general, how many electrons I have? It's pretty simple. What if there is no charge? I'm just saying, in general, in this box, how many electrons does carbon have? 6. How did you figure that out? Same as the protons, all right, which is the atomic number, okay? You're overthinking the question. It's a Monday. That's okay. So, guys, below it, whatever you see in your dash configuration should add up to the total number of electrons, okay? Because it's an electron configuration. You can only work with however many electrons you have. So keep that in mind. When you run out of electrons, your configuration's going to end because you don't have any more electrons to worry about, okay? You with me so far? So now, notice how there's two different sets of numbers here. We have a 2 and a 4. Okay? These correspond to energy levels. We're going to talk more about energy levels, guys, in just a couple minutes. But here would be one energy level, then this would be the next energy level. Okay? So everywhere you see a dash, you have a new what's called energy level. The way you want to think about it is think about it like it's a ring. Okay? A ring around the nucleus. Now, this looks like Bohr's model, which is not exactly what we use today, but it's an easy two-dimensional drawing that we can do. Each ring, guys, is a different energy level, okay, where the electrons are most likely located. Think about it like the solar system, okay? So you would have electrons on there. Now, we are going to get into drawing Bohr diagrams maybe today, otherwise tomorrow. So we'll kind of come back to it. But that's what this is kind of showing you is that, hey, these numbers correspond to the number of electrons and what level or ring they're located on. Now, the first step before we start drawing pictures and thinking about it is we're just going to write down configurations. So magnesium. Where might I look for magnesium's configuration? Right, below the atomic number. So on your reference table, on your periodic table, what's the configuration, guys, for magnesium? 2-what? 2-8-2. Now, Mason, you're absolutely right. There are 12 electrons. And when you take a look, guys, at this configuration, 2 plus 8 is 10, plus 2 is 12. That's it. So when you're asked to write a configuration, they give it to you. It's that simple. Okay? Now, the next substance, though, is Mg2+. So let's take a step back before you start writing down the configuration. That 2+, that means it's a what?
It's charged.
Okay, it's charged. What do we call a charged atom? Ion. Now, what type of ion is this? Let me ask you that. So it's positive. What do we call a positive ion? Got to know this for tomorrow's quiz. Cation. Good. Were you the one last week that said anion? And yep, I knew it. So, yeah, cation, guys. A positive ion is a cation. Remember, it's got that T that's in the middle that looks like a plus sign. So this is a cation. Now, what happens in a cation that makes it positive? Like physically, what's happened to that element, to that atom? Yes, it has less electrons because it has lost them. So it's lost how many in this example? 2. So it's going to have a very similar configuration, guys. Mg2 plus should be similar to magnesium, but how many electrons will it change by? 2, and it's going to lose them. So what do you think our new configuration is going to be? 2-8. Because if we were to write this out, guys, we would have total protons would equal 12, and our electrons would be 10. All right, which 2-8 means we have 10. Okay, that's what we're doing with those electron configurations. They're not that difficult. Don't make them harder than they need to be. All right, I want you guys to go through and try these next 3. Leave lead, but try the next 3. Who can tell me bromine's configuration? 2-8-18-7. How is the bromine -1? So now, what do we call a negative ion? An anion. Okay. If it's negative, what does that mean it's done with its number of electrons? It's added 1, right? It's gained it. It's brought it in. How's that going to affect this configuration? What number is going to change? 7. The last number, guys, so remember that. The last number only with an ion will change. So 2, 8, 18 is going to be the same. And what's my last number going to be? It's going to be 8 because it brought in 1 more electron. Okay. So remember, just as a quick trick from last week, if you see a plus sign, guys, you're subtracting from your overall charge. If you see a negative, you're going to add to the number of electrons, or to the number of protons to get your electrons. Okay. Barium. What's barium's configuration going to be? They get pretty long, don't they? Lead has a total number, guys, of 82 electrons. So it's pretty long there. So there's a shortcut. If you take a look, find number 82 on your periodic table. That's lead. What do you notice that's different about that configuration they give you versus the other ones? What does it start with? A dash, right? So what they've done is just cut off the first 2 levels, and they're just writing the last ones, just to shorten it up a bit. So what's lead's going to be? Dash what? 18-32. Okay. So guys, when you're asked to write them down, you're just writing what you see on your periodic table. Okay. They take a lot of the guesswork out of it. All right. Dash 4. Oh my goodness, I can't hear or speak today. Valence electrons are the most important piece that we will use all throughout the year, especially when we come back and start talking about reactions and we start talking about bonding. Valence electrons are the ones that are doing everything. Guys, valence means outer or outermost electrons. Okay, so that is the last number that's in your configuration is what you're going to be looking at. Kernel electrons are all the inner shell electrons, the ones that are not at the end. So you might be asked, well, how many valence electrons? So give me the configuration for chlorine really quick. Configuration. The electron configuration for chlorine. Okay? 2-8-7. So if I'm going to look for my last number is what? Bam, there's my number of valence electrons. Okay, I've got 7 valence electrons. How many kernel or inner electrons would I have then? That's everything. Exactly. That's going to be everything else. So valence are what I circled. Kernel are what I boxed. So how many kernel electrons are there? There's 10. Okay. So the very last number represents your valence electrons. When we do our periodic table unit, in a couple units, we'll talk more about how you know that and why. Okay, and when we get into bonding, it's going to make more sense. So right now we're getting the basics. We will get into the why behind it a little bit later on. I want you guys to do nitrogen and sodium. Nitrogen's going to have 5 valence electrons. How many kernel ones? 2, right? So it's going to change based on the element. Each element's going to be different. Some will be similar, but they can, like in terms of kernel, but valence will be different. Sodium has how many valence? How many kernel? Okay. Pretty easy. You're like, well, what's the catch here? How is this going to get harder? Okay. Guys, not everything always gets super harder. Okay, so just keep that in mind. Now we're going to kind of talk more about these things called principal energy levels. All right, so this is on the next page in your notes. And Peter, this is kind of going along with what your question was. So guys, a principal energy level is just an electron energy level that consists of orbitals, which are designated as S, P, D, and F. Now, we're not going to get into the specifics of these. Again, they're homes where the electrons are. So if you have a house, is there usually just one room in a house? No, you've got multiple rooms. So think about the house as like the principal energy level. Inside that house, you have different rooms. These letters are different rooms, different spots where the electrons can be hanging out. Does that make sense? All right, it's just different rooms within a house. We're going to just start by our configuration. Mason.
Are the electrons like...
So let's start with the configuration. What's our configuration, guys, for helium? Was it? 2. Okay, so how many total electrons do we have there? 2, right? Not a trick question. So when we talk about these energy levels and when we talk about these orbitals, which again are like the rooms within a house, okay, on the New York Regents exam, they're not going to necessarily have you memorize it. If you saw something like this, they would give it to you, and it's going to follow this same pattern that we're going to see right here. Your task would be to kind of visually show those electrons and what they look like. So we know that for helium we have 2 electrons. How we represent electrons on these lines, which are representing the orbitals, we draw arrows. Okay? One arrow is for one electron, the other arrow is for another electron. You with me so far? Okay. Notice what I did here? What did I do with the arrows? Now, I know they don't look like arrows, so maybe let me just start right there. Okay? There's one arrow, there's another arrow. Sorry, the other way was just a shorthand way of drawing arrows when you do them over and over again. Those arrows, guys, represent electrons. We said, how many electrons does helium have? 2. How many arrows do we have right here? 2. Those are both of the electrons that helium has. And you may be asking, well, why is one arrow? Why are they even using arrows? I don't know. That's just been the symbol that they've used forever. One is up, one is down. Okay? Let me ask you this. If I gave you the option of running a marathon or staying in bed, what would you choose? Everybody would choose staying in bed. Only crazy people, right, would say, I'm going to go run a marathon. Apparently that's you, Corden? No? Everybody keeps looking at you. Anyway, everybody's going to stay in bed. Why? Because we are lazy. Electrons are lazy as well, guys. Okay? They want to use the least amount of energy possible. So what we do when we show this visual right here, one of those is up and one of those is down to be in a lower energy piece. Okay, that's really kind of the simplistic way I can say it. So like Mason was asking a couple minutes ago, are electrons moving? Yes, they're spinning all the time. One is spinning counterclockwise, the other one's spinning counterclockwise. That is lower in energy than them both going the same way. What did we say with electrons? What's their charge? Negative. What do like charges want to do? Nope. They want to repel each other. You're the second person to say create a positive, and I don't know where that's coming from. All right. What's that? Oh, okay. Yeah, okay, I can see that. 2 negatives multiply. I get that. But no, they want to repel each other, guys. So by them spinning in opposite directions, they're going to kind of be okay with each other. So they're going to be closer together. Again, I'm simplifying something, guys, that's a little bit more complex. Don't worry about it. Follow the pattern. All right, let's move on to carbon. This is going to be a little bit more complicated. What's our configuration, guys, for carbon?
2-4.
Okay, 2-4. That's not my pen. How many total electrons do I have here? 6. Now, before you start freaking out, guys, and start thinking, this is where I lost the last class as well. This is given to you. So now, we have more electrons, right? So we have more energy levels, more space that those electrons are going to take up. Okay? This is shown to you. First energy level is always 1s. When we go to the second energy level, we have a 2s and a 2p. Different rooms. Think about it like a house, okay? You've got the first floor with one room. Then you've got the second floor that has two different rooms within it. Okay? And we can keep going on. Each floor has got more rooms. All you're trying to figure out is where the electrons are going. So we have 6 electrons. You start with the lowest number and you move up from there. Fill it in. 1, 2. They've got to be opposite.
Does the first row always go up?
You could put the first one down if you want and the second one up as long as they're opposite. So it doesn't matter if you start down and then go up, as long as when they're in the same line, Miriam, they're opposite. Okay? Then we're going to fill in, guys, with a 2s. I'll show you that. Down, up. Okay? How many electrons have I used up until this point? 4. How many more do I have to use? 2. Now you've got options, right? You can put them in any of those 3 lines. But the thing is, guys, let me ask you this. If you had the option of sitting in a car with somebody, or like a back seat, or even a desk. Let's go to that. Even keep it simpler. If you had the option to choose like these first 3 desks, if somebody's sitting at this desk, say you don't even know the person, would you sit next to them or would you go to one of the other empty ones? Probably empty ones, right? You probably fill in like that until every single desk has 1, and then if you don't have any options left, you're going to go back and double up. Same idea here, guys. These electrons, they want to spread out. They won't want to be next to each other. They'll spread out. So we have 2 more electrons. We can put them anywhere we want. But they're going to spread out and take up every single line first. Then they'll go back and double up when they have to.
Why are the letters SPP?
As well. You're not going to have to do a lot of this, guys. So don't get hung up. It's just kind of introducing it to you so that you don't get too lost with it. So you're probably like, well, I'm already lost. Breathe, okay? Just like with stuff we did last week, we came back and you guys were all good on your quizzes. Right? Your quizzes showed that. What's our configuration for sulfur? 2-8-6. So think about it. How many total electrons do I have to work with? 16. So here's another way to think about it. Notice in helium, we only had 1 number. So there was 1 line over here. There was just this 1 spot. Carbon, we had 2, right? Here's 1 of those lines. Here's the other one. Sulfur has got 3 energy levels. Notice we have 1, 2, 3. So when we go from our configuration over here to the letters and drawing on these arrows, okay, 1 has got 1. The first one has 2. There's 2 electrons. The second energy level has 4. 1, 2, 3, 4. Notice how they pair up. Okay. Where are these 2 going to go in my arrow or my letters or my lines? Yeah, right? One's going to be up, one's going to be down. Doesn't matter if you go down then up or up then down. So those 2 are gone. The 8, where's the 8 going to go? Line 1, 2, or 3? 2, right? Fill your S in first, then your P's come along. Up, up, up. Then I'm going to go back and double up. Down, down, down. You could have went down, down, down. You could have went down, up, down. It doesn't matter again as long as when you get 2 on a line, they're opposite. Okay? And then the last one, how many arrows should we have here? 6. Now notice, guys, before you start drawing these in, when I introduced carbon, okay, I went in until I ran out. But notice, which one did I fill first? I filled my S's before I went on to my P's. So, of course, that's going to do that. So now, when I filled in my S first, then I went on to my P's, what do you think we're going to fill in? What's the order down here that we're going to fill in? S, fill those up first, then we're going to fill up the P's, then we'll go on to the D's if we have enough electrons. Do we have enough electrons to fill all that here? No. So we're going to fill my S's. There's 2 of my 6. There's 3, 4, 5. Do you think it matters where I put the 6th one now? As long as what? It's opposite. So I'm going to put it right there in the middle. I could have put it to the left. I could have put it to the right.
So you didn't have to put it in 3D?
No. We got to, so we fill up our first letters first. Then if you have enough electrons, you move over there. But we ran out of electrons. So if we had more electrons, we would absolutely keep filling until everything's filled up. But we ran out. Once you run out, you're out. So your big task, and I have seen this on the Regents exam, it'll ask you, in the second energy level, what's the maximum number of electrons that can be held? You're going to use this little formula, 2n squared. N just means principal energy level. That's the symbol that's used for energy level. So if your energy level, guys, is 1, you're going to plug in a 1 for n. So if we take a look, 2 times 1 squared. What's 1 squared? 1 times 2 would be 2. So the first energy level, guys, can hold 2 electrons. If you have an element that has more than 2 electrons, you then have to go on to a new energy level. Principal energy level 2. What's 2 squared? 4 times 2 is 8. So the second energy level, guys, can hold up to 8 electrons. So if you put the first level together and the second level together, the total you can hold then between those two would be 10. 2 plus 8 is 10. So those go up through element neon. If we take a look back here on our last slide, guys, take a look. All right? Each line can hold 2 electrons. There's 2, 4, 6, 8, 10. Oh, it can hold up to 10. Then we had to go on to another one. 2, 4, 6, 8, 10, and so on. So continue that pattern. What's 3 squared? 9 times 2 would be? The third energy level can hold up to 18 electrons. 4 squared is what? 16 times 2 is? Okay. So what you need to remember is this little formula, guys, right there. 2n squared. When they give you an energy level, you're going to square it and multiply it by 2. That will be your total number of electrons. That you very well could see in June. We will come back and review that. Okay, so you guys don't, have to... I'm sure you will not remember that throughout the entire school year. I get that. All right? So your homework tonight is you're going to